So as a first example, let me start with the simplest case I could imagine. Calculate the length of the circle of radius r. Okay, so I have a circle of radius r, which is my curve. So this is my curve C, and I'm asking you to calculate the length of this curve. So we already know that the length is 2 pi r, but let's see if we can arrive at it by doing a curve integral, a line integral. Okay, so we want to find the length by doing the line integral over curve C of dl. Remember that the length can be calculated by integrating dl, which is the same as having a implicit integrand of 1. Yeah, it's like having a 1 here. So first step is to parameterize the curve. And the way I'm going to parameterize our curve is we need to find a vector as a function of some parameter, and I'm going to call this parameter phi, because it's going to basically be the angle. Yeah. So of course this vector is x of phi and y of phi. We're in 2 dimensions, so we only need 2 elements in vector r, and these 2 functions are going to be r cosine phi and r sine phi. This is the well-known way to parameterize a circle using polar coordinates. Okay, and what are the limits? So phi goes between 0 and 2 pi. So that's step 1. Step 2 is to find dl. Okay, so how do we find dl? So one way to find dl is to use the recipe. So this is dr over d phi, the norm of the tangent vector multiplied by the differential of the parameter. Okay, remember this is the recipe to find dl. Yeah. So what steps do we need? First, we need to calculate the derivative of r with respect to phi. So we have r here. We need to calculate dr with respect to phi. And this is going to be a vector, which is going to be minus r sine phi and r cosine phi. Okay, I simply did the derivative of the 2 functions for x and y to find this tangent vector dr over d phi. Now, don't forget, you need to calculate the norm of this vector. Okay, so the norm of dr with respect to d phi. So the norm of a vector is the square root of the squares of the components and you can immediately see that this will be square root of r squared times sine squared plus cos squared, which is equal to 1. So we end up with the square root of r squared, which is equal to r. Okay, so therefore we can now substitute that dl is equal to r times d phi. Okay, so we found dl. Now we could have found it geometrically. So this was with method 3, but we could also have used method 2 geometrically. So how does it work geometrically? So we have to picture we are on the curve, yeah, so our circle, and we increase phi by an amount d phi. So what is the length of this segment here when d phi is a differential increase? So this is our r, and this segment dl is equal to the arc length, which is the radius times the angle, so it's r times d phi, which perfectly agrees with what we got using the recipe. And finally, we could have looked it up using a table, right? In practice, you don't have to do all of this. You just choose one method and do it, okay? I'm just doing it as an example so that you see how all the methods work. So let's go to the table, which I do provide in the exam. So now we are interested in polar coordinates. I don't have a row for polar, but I have a row for cylindrical. And it's the same thing, because you know that cylindrical coordinates include polar coordinates if you just ignore the z component, okay? So every time we see dz, let's cancel that out, okay? So we are only left with these 2 components. So now my question would be, what is our parameter? Is it rho or is it phi? Our parameter is phi. We are changing the angle, okay? So d rho is 0. We are not changing the radius. So d rho goes to 0, so this goes to 0. So we are only left with this term, which is rho times d phi times some unit vector, because this is giving us the vector dr, which we will use later. Okay, later in the chapter you will see when we use vector dr. But for now we are using the scalar dl, which is just the norm of the vector dr. So we are left with this, we calculate the norm, so it's rho times d phi, which is exactly what we found in the other two methods. Okay? So we are always back to the same thing. Very good. Third step is to evaluate the integrand at the curve. Now this is a bit strange because our integrand is simply dl, so there is nothing to evaluate, we just have dl equals r d phi. So sanity check, is this a function of the parameter plus constants? Yes, we only have r, which is a constant, and d phi, which is the differential of our parameter. So everything is correct. So now we are ready for step 4, which is calculate the integration. So the way we do that is we have our integral of dl, which now we can write as the integral of r d phi. And what are the limits for phi? So the limits for phi are between 0 and 2 pi. So therefore, have to calculate this integral, which is very simple, right? So this integral is simply r squared. Sorry, no, not r squared. We're integrating with respect to phi. So this is r times phi, evaluated between phi equals 2 pi and phi equals 0, which gives us 2 pi r. Okay? And that's it. So we have derived an equation for the circumference of a circle using a line integral, following our step-by-step recipe. I repeat that this was a trivial example. This would be too easy to ask in an exam. It's just for you to get a first example of a line integral. Let's do some more interesting and complex examples.